Hey guys, how's it going? It's the Black App here, bringing you a little different video today. This is in Minecraft, but I'm going to be showing and explaining this 4-bit adder and subtractor that I've designed and created in Minecraft. I haven't finished the display, but basically what this allows you to do, I'm just going to give you a quick example. Let's switch this to addition, and let's add 3 and 3. That should be 6. So if you come here, the display would be 10's place. That's a 0. 1's place is a 6 there. So that, along with the output here, should be correct. Let's look for the light that's on. That's over here. And 6. That is correct. So as you can see, the adder works. And now let's switch it to subtraction, and it's yellow minus red, so let's 3 minus 2. This might glitch out a little bit because I switched a bunch of levers at the same time, but should be 1. And if you come down here, it will be 1. All right. So I know this looks a little, it potentially looks a little frightening if you don't really know what's going on here. But my goal in this video is going to be to explain a little bit of the basics behind why this works and how I got this to work. So basically, I'm going to go over some of the basic logic gates. Then I'll go over the idea behind truth tables. Then I'll get into a tiny bit of Boolean algebra. And then at the end, just to explain how this works, we will have to go into encoders, decoders, and adders. Both the carry look ahead and ripple carry adder. Now I know that sounds like a lot. It's really not, and I will chop it up for you guys real quick. So first off, I'm just gonna, like I said, first off, gonna go over some basic logic gates, and I'm actually gonna go into Paint here to show you how this works. So you've got 3 basic logic gates. You've got the NOT gate, which looks like this. So basically, if you have a 1 going in here, you'll have not 1 going out, which would be 0. And that's a very important thing I might have skipped over. If you don't know, this is all based in 1s and 0s. It's digital design, so it's either 1 or 0, always. And then the next gate you have is an AND gate, which looks like this. So there's 2 inputs and only 1 output. Let's say the input of this one, also I'm just going to go back here just for a second. When I get into Boolean algebra, the symbol for this is kind of like that apostrophe there. And then for the AND gate, it would be A plus B. If this was A and this was B, this would be A plus B. And then you have the OR gate, which looks like this. Again, 2 inputs, 1 output. Let's call it A, B. This output would be A dot B. And just to explain these a little bit better, I'm going to go into truth tables. So basically, when you have these 2 inputs, you have a 2-bit system, which means because it's a 2-bit system and binary is a base 2 number system, that means you take your number of bits and raise it to the power of the system. So 2 raised to the power of 2 because it's a 2-bit system, which means you will have 4 possible combinations. All right, just a quick correction. I got completely wrong. This is really embarrassing. But when I was talking about how many possible combinations there are, based on how many bits there are, I said you take the number of bits and raise it to the power of 2. So if you have 2 bits, you raise it to the power of 2. That is very incorrect. Don't do that. All right. It is 2 raised to however many bits you have. So let's say you have 4 bits. That's 16. That's how that works. Not this way. That's wrong. This is correct. Do it this way. Oh, man. Combinations. I'll draw these out here. So those are your 4 possible combinations when you have A and B. So I'm not very good at drawing. This is getting a little messy here, but so A plus B for the AND gate here, when A is 0 and B is 0, the output, A plus B, is going to be 0. And this is exactly what a truth table is. A plus B is 0 when A and B are 0. When A is 0 and B is 1, the output is also 0. Same for here. So that means when A is 1 and B is 1, the output will be 1. So basically, for A plus B to be 1, A and B both have to be 1. Now you go to the OR gate, A dot B. That means when either A or B are 1, the output is 1. So here in the first case, 0, 0, that means it's 0. 0, 1, that means it's 1. 1, 0, here, that means it's 1. And again, because they are both 1, the output is 1 because, yeah, it kind of makes a little bit of sense. They have another gate called the exclusive OR, which means that would be 0, but we're not going to worry about that right now. So those are 3 basic logic gates. Their symbols in Boolean Algebra and the truth table that goes along with it. And now I'm going to show you a little bit of why Boolean Algebra is useful. Now, Boolean, if you don't know, basically means that there's only 2 states, either true or false, which equates very well to 1 or 0. I'm going to make a new one here. Actually, I got a little room over here to the side. So let's say you have a circuit that looks like this. Let me just draw this real quick. Oh, that should be an OR gate. Sorry, I drew this out beforehand. All right, so let's say you have an OR gate. I'm back. You have an OR gate here. And yes, this is A and B. And then you have another OR gate here. And this is A and C. And you put them both into an AND gate at the end. This output here is A dot B plus, so that's that first one, plus A dot C. So those are where the OR gates are. This is the AND gate. So you just go straight through A or B plus A dot C. That's the output. Now when you look at this expression here, I'm sure some of you will notice there's a way to simplify this. And that is just saying A parenthesis B plus C. And basically this will actually be a simplified version of this circuit here. And what this looks like is you got B plus C, so it's an AND gate. And it goes into an OR gate with A. And that is why Boolean Algebra is helpful, because you can simplify circuits using it. And there are a lot more properties similar to this one. Oops, didn't mean to draw a line through that. A lot more properties similar to this one. This is just a very simple one that a lot of people will know just from regular algebra. But we don't really need to get into more complicated than that. I can, if somebody wants to know more about this, I can make more videos on that. Just comment down below saying so, and I would be happy to do that. So now I'm going to explain a little bit about decoders and encoders. And it's actually probably going to be easier to do that in Minecraft. So let's go here. I actually did set up a pretty good encoder, I believe, over here. Yeah. All right. First off, I guess, yeah, I'm going to show you just how to make an AND gate, just to help you understand a little bit. That's not what I need. I need this. Let's go like that. This is what an AND gate in Minecraft looks like. Usually, I should just grab a lever. Sorry, not really set up for this. Kind of decided to do this last second. All right, yeah. So this would be an AND gate, which means, let's say this input is 1, and when this input is 1, then the output is also 1. But if either one of them is not 1, the output is a 0. Here's an OR gate. It's very similar, but actually more simple. Yeah, all you need is that right there. So when either one of them are on, the output is 1. And when they're both on, the output is still 1. And then here's also a NOT gate. I'll show you that too. Wait, is that... I think I set that up wrong. Oops. Okay. So right now the input is 0, which means the output is 1. Input 1, output 0. And that's basically what you need to build a decoder. But I'm not really going to go into the specifics of the decoder. You can see here I have a bunch of AND gates of different types with NOTs in them, but I don't really need to get into that. And I'm just mostly explaining the concept. And basically, what that is that when you have a 4-bit number like this, that's glitched out a little bit. The first bit has a value of 1. The second bit has a value of 2, and it just doubles. So 4, 8. If I had a 5th bit, it would be 16. And so when I flick this first lever here, the display will be 1. And if go to the value of 2 here, and if I wanted to display 3, it would be 2 plus 1. And that's 3. You can go all the way up to 15, where if you select all the levers, there's 15. And basically, you have a bunch of AND gates, and at one time, only one of these 15 outputs can be activated. At one time, only one of these outputs can be activated, and this is just the display for that. That's nothing to do with digital design. That's all Minecraft stuff. And so typically, how that is shown would be like this. So if you got a decoder here, you have 4 bits going in, and you have 0 through 15 bit outputs. Just, yeah. And then an encoder is the exact opposite, where you have 16 inputs going from 0 to 15, and you get 4 out. And basically what that means is over here, let's see, need to change that. Sorry. Over here, I should have set these up closer to each other. That's what this is. This is an encoder right here, where I can select one of these 16 inputs and get 1 output. And this is actually, it's a little more complicated. It's a priority encoder. Basically what that means is that it will only select the highest digit, highest value digit that I select. So if I have 8 and a 2 selected, it'll only select the 8. So I have 8 selected right now, which means that this line is activated. And if you come here, oh, it's on subtraction right now. Sorry. Let me just switch that back, and I'll explain why that's important. You can see that it's 1, 0, 0, 0, and if you remember, the first bit had a value of 1, then 2, 4, and 8, which means this 1, 0, 0, 0 has a value of 8. And I'll actually, down here, I think I made, yeah, this is a basically what a 4-bit truth table looks like, where 1, 2, 4, and 8, and there's 16 possible combinations. And so what's nice about when you set it up like this, and you can see that pattern where you start out with 8 zeros, 8 ones, then 4 zeros, 4 ones, 4 zeros, 4 ones, and you just go in half, 2, 2, 2, 2, excuse me, and then 1, 1, 1, 1. What's nice about it when you set it up like this is this actually goes from 0 to 1, 2, 3, 4, 5. It actually just counts up all the way to 15. And that's what's nice about setting it up like that. All right. So that's encoders and decoders explained slightly. So that's what this is here, an encoder and an encoder over there. So that when I select one of those 16 levers, there's actually only 15 because obviously I don't have a lever for 0. One of these 15 levers or 16 possible outputs, I get a specific 4-bit output after that. And then it will either add or subtract those two numbers. So that's a little bit of how the binary system works. So now that I explained the 1, 2, 4, and 8 system like that, I'll show you how to add two 4-bit numbers. Let's go back to Paint here. All right. So let's say you have two numbers. Let's say you got, I'll just do it in base 10 right now. So you want to add 3 plus, let's see, what do I have down there? That's 5. You want to add 3 plus 5. Well, what is 3 in a 4-bit binary system? Well, if you assign the values 8, 4, 2, 1, like that, 3 would be 2 plus 1. So that's just 0, 0, 1, 1. And 5, just going to go like that, would be 4 plus 1. So 0, 1, 0, 1. When you add these together, this is just something you kind of have to memorize, is that 1 plus 1 is actually 0, and then you carry a 1. So there's a carry line up here. So again, 1 plus 1 plus 0, it's 1 plus 1. So 0, carry 1. And again, 1 plus 0 plus 1 is 1 plus 1, which is 0, carry 1, which is 1. 1 plus 0 plus 0 is 1. And if you look at that, that lines up with the 8 value. So this actually this equals 8, because it's 8 plus 0 plus 0 plus 0, because these all have that system there. And obviously 3 plus 5 is 8. So this is correct. And let's say you want to add, there's another little trick that you should know when adding. It's possible to run into a 1 plus 1 plus 1, and I'll show you what happens there. Let's say you're adding 6 plus 6. Again, let's go 8, 4, 2, 1. Well, how can you get 6 here? It's 4 plus 2, so 0, 1, 1, 0. Plus 0, 1, 1, 0. Obviously 0 plus 0 is 0. 1 plus 1 is 0, carry 1, if you remember from last time. And then 1 plus 1 plus 1, like I was saying, is a special scenario you can run into. This is actually just 1, and then you also carry a 1. And then this is 1 plus 0 plus 0, which is 1. And if you look at that, 8 plus 4, because those are the ones assigned to that. So that equals 12. Which of course 6 plus 6 is 12. Now here, I'll keep it here. Now I'm going to show you how to subtract. Let's say you want to subtract 10 minus 5. Well, let's do the same thing. That's obviously 5. I'll just go ahead and write that down right now. 8, 4, 2, 1 there. So 10 is 0, 1, 0, 1, because again 8 plus 2 is 10. Minus 5, 0, 1, 0, 1. Well, it's actually way easier to add than to subtract. So one thing you can do, which is, well, the best thing you can do, honestly, is you take this second number here, the number that you're subtracting, and you flip the bits and add 1. All right, you just got to remember that. Flip the bits and add 1. And then you can add those numbers. So 0, 1, 0, 1, which was the 5. You flip the bits. So you get 1, 0, 1, 0. And then you add 1. 0 plus 1 is 1, and then all the rest are the same. So this is the number that you're actually going to be adding. So now you're actually adding 1, 0, 1, 0, which was the 10, plus this number, 1, 0, 1, 1. which is 1, 0, carry 1, 1, 0, carry 1, 1 plus nothing is 1. But when you're actually subtracting, you can forget about this one. And so that leaves you with 0, 1, 0, 1. And when you assign the 8, 4, 2, 1, that equals 5. Like I said, 10 minus 5 is 5, and that's the answer that we get. So that is that's a crash course on how you add and subtract in binary. And so basically when you're adding 4-bit numbers in a system, you just do one of these at a time. But the carries are where some problems can occur. And there are basically two different, at least to the best of my knowledge, I only took one college course on this. There are two basic kinds of adders. There is the carry look ahead adder and the ripple carry adder. The ripple carry adder is actually a lot more simple, but it takes way longer. And I'll just throw a quick picture of them from the internet on up there. So there's a ripple carry adder, and then there is a carry look ahead adder. I don't know what I'm doing here. It's probably trying to explain something to a friend. But this is basically a ripple carry adder here that I set up. And ripple carry adders, like I said, they're simpler, but they take way longer because it adds 1 bit to 1 bit, and then it takes the carry and adds that into the next one. You basically add each bit at a time, one by one, and it takes a long time. The benefit of the carry look ahead adder, which is what I used on this adder over here, it's a lot more messy, as you can see. It's a lot more complicated to build, especially in Minecraft. But the carries is all determined. I can't remember exactly, but I believe it's by like the first edition of the first bits. And so basically it adds that right away and gets it into the rest of them, into the rest of the adding. And maybe if I can find a diagram of a ripple carry, or sorry, a carry look ahead adder, I'll throw that up there. And it's just way faster, and that's why I did it for this system, just because it was way faster, and I hadn't built one before, so I thought it would be cool. So yeah, at this point now, you know, here's the encoder, and the encoder over there. Here is the carry look ahead adder. It's this mess here. And then this actually, once you get that input, or sorry, once you get that output, that's this here. And there's a total of 5 bits because it can add up to 30, which would have to be a 5-bit number because like I said earlier, 4 bits only have 16 possible combinations. So in order to get up to 30, you'd have to have 32 combinations, and that's what a 5-bit number does. So once it gets these 4 or 5 outputs, that goes through this decoder here, and it gives you an output, which right now is nothing. And why is that? 3 plus 8 is 11. Why is 11 not? Maybe it was, and I just didn't see it. Oh, it is. There we go. 11. Perfect. So there you go. There's a crash course. Oh, here. This is actually just where I flip the bits. So you can see right now, the output is 1, 0, 0, 0. Flip it to subtraction. So that means these bits are gonna flip 0, 1, 1, 1. So you can just see they're the exact opposite. And then this is where this is flipping the bits, and then this is adding 1. This is going into the first carry. So yeah, there you go. There's a crash course on how to build an adder subtractor in Minecraft. Leave a like if you enjoyed. Comment if you want me to explain this in further detail, or if you think I should never explain anything ever again, because I'm terrible at it. Yeah, let me know.